Today we're going to look at geometry and trigonometry. So we'll start by looking at the area and volume of several geometric figures, starting with the triangle. Now let's consider a right triangle shown here in the diagram. So we've got a 90-degree angle there. Now first, looking at the area of the rectangle is the base times the height. And so if you slice this rectangle down the diagonal, here we have half the area and here we have half the area, and so we can clearly see that the area of the triangle below is 1/2 the base times the height. So it's not too difficult to formulate a formula for the area when we have a non-right triangle as well. Suppose that we have three vectors, v1, v2, and v3, and suppose that v3 is equal to v1 plus v2. Let's let the norms of v1, v2, and v3 be a, b, and c respectively. So just as we have in the diagram on the following page. Okay, now what I'm going to do is set out several intermediate vectors that add up to some of these. So first of all, P, which will be this one. So this is P. And then over here, suppose we have a vector Q. Now notice what we have here is that v1, which is this whole thing, is equal to the sum of p plus q. This one over here is v2, and this one here is v3, which notice v1 plus v2 gives v3 by the way that's sketched. So that's another fact that we have. Okay, so we've taken P to be the projection of v2 onto v1. Now let's let R be equal to, well, that would be v3 minus q, or no, q minus v3. Okay, R is perpendicular to v1, so that P plus R, let's check, P plus R, now R would go this way, is equal to minus v2. Okay, so that's another fact. P plus R is minus v2. Alright, so given all these three, let's begin to calculate the area of this triangle. Now we've chosen R to be perpendicular to v1, so that the area of this triangle shown here is the sum of the areas of these two right triangles. So in other words, the norm of P times the norm of R divided by 2 gives the area of this triangle on the right. And I don't know whether I said divide by 2, but at 1/2 the norm of P times the norm of R gives the area on the right. Now 1/2 times the norm of Q times the norm of R gives the area of the triangle on the left. And obviously the sum of those two right triangles gives the area of that entire triangle. So we have sum of these two halves here. Okay, so what we can do is factorize out 1/2 and the norm of R, and what remains is the norm of P plus the norm of Q. Okay, so the sum of the norms of P and Q add up to the norm of V1, and that's simply because P and Q are lined up like this. And then this is V1. So in other words, V1 is equal to P plus Q. P and Q are parallel, so the sum of these two norms is equal to the norm of V1. Okay, so we end up with this for our area of the total triangle. Now we just need to find a formula for the norm of R. But fortunately we can just use that sine of angle C, which is right here, is opposite on hypotenuse. Okay, so that's sine of C is opposite, which is the norm of R, over the hypotenuse, which is the norm of V2. And so we can write that the norm of R is equal to the norm of V2 times sine of C, and just substitute that in there. And so we get this nice formula for the area of the total triangle A. Okay, next what we can do is replace the product of the norm sine C with the norm of the cross product. And so we'll just get this formula. The norm of the cross product of V1 with V2 is the product of the norms of V1 and V2 sine of the angle between V1 and V2. Okay, so that gives us, via substitution of this in there, we have that the area of that triangle is 1/2 the norm of the cross product of V1 with V2. Okay, great. Another nice formula for the area of a triangle is due to the Alexandrian hero known as Heron's formula. And it says that the area of a triangle squared is the product of these three, or these four, S times S minus A times S minus B times S minus C, where S is 1/2 of the sum of the three sides. But let's have a careful look at this formula. And to do that, I'll grab some paper, bring this down. Okay, so let's draw a little triangle here. So this side will be A, this B, and this side C. That'll be angle A, this will be angle C, and this will be angle B. Okay, now Heron's formula states so when we take this and sub it in here and then multiply throughout by 16 so that we clear the 1/2 denominators in each of the four terms, what we end up with is 16a squared equals a plus b plus c times b plus c minus a times a plus c minus b times a plus b minus c. Okay, so what I want to do is express this somewhat differently before I begin to demonstrate that it's true. So let's bring together this and this. Now we have a difference of two squares. So this is a plus b. We've got an a plus b over here, a plus c and a minus c here. So we can write that part as a plus b squared minus c squared. And then this part right here we can write as c squared minus, in brackets, a minus b squared. Okay, now if we expand each of these two squares, then what we have is a squared plus 2ab squared plus b squared minus c squared. And then if we do the same thing here, then we have c squared minus a squared plus 2ab minus b squared. Okay, and so this we can represent as hang on, that shouldn't be squared there, 2ab plus a squared plus b squared minus c squared. And then this one we can write as 2ab minus a squared plus b squared minus c squared. Okay, good. And then now we can see that this has the same thing there, and so we can view this as a difference of two squares. So this one times this one is 4a squared b squared. This times this gives us minus a squared plus b squared minus c squared squared. Okay, and this is 16a squared. So far we've just rearranged Heron's formula. So next what I want to do is use the cosine rule. So the cosine rule that we demonstrated previously says that c squared is a squared plus b squared minus 2ab cos of c. Okay, so we can rearrange this and write cos of c is a squared plus b squared minus c squared over 2ab. Now since cos squared c plus sine squared c is 1, it follows that cos of c is the square root of a squared, well, 1 minus c squared, right? So let's write that first. So 1 minus sine squared of c. Okay, just rearranging this. This should say 1 minus sine squared of c, square root. Okay. So we'll sub this in. Hang on, I really want the other way around. So let's get rid of this. What I want is sine of c equals square root of 1 minus cos squared of c. Okay, so this is a rearrangement of this. And so we want to sub this in next. And so when we do that, we get 1 minus, in brackets, a squared plus b squared minus c squared all over, and that's squared, right, because we're squaring the cos. And if we square 2ab, we've got 4a squared b squared. So if we put this under one denominator, we'll have 4a squared b squared minus, in brackets, a squared plus b squared minus c squared squared all over the square root of that denominator, so 2ab. Alright, so this is sine of c. Okay, finally, from the cross product, so a is 1/2 of the norm of v1, v2 sine of c right? So that's what we got from the cross product formula. So then this says this is 1/2 of AB sine C, but that's equal to 1 on 2AB square root of 4A squared B squared minus, in brackets, A squared plus B squared minus C squared squared. Okay, so we can cancel the AB there, and we have 1 on 4. Multiply the 4 on both sides and then square the result, and we get 16. A squared is 4A squared B squared minus, in brackets, A squared plus B squared minus C squared squared, which, remember, was our second form of Heron's formula. So which is Heron's formula. Okay, and that completes the proof of Heron's formula. Okay, so there's another way to express Heron's formula using a determinant of a symmetric 4x4 matrix. Now it's symmetric because if you transpose it, you have the same matrix there. But this is just incidentally. So let's have a look at an example of Heron's formula to calculate the area of a triangle with sides of length 10.3, 9.5, and 7.2. So we would first add up those sides and divide by 2, and when we do that we get 13.5. So Heron's formula gives the square of the area as 13.5 times 13.5 minus 10.3 times 13.5 minus 9.5 times 13.5 minus 7.2. And so we get 1088.64. Now taking the square root gives us that the area of that triangle is 32.9945 units squared. Okay, so representing that result with two significant figures, for example, if we wanted to, then we might call that 33 units squared. Okay, let's move on to the volume of a truncated cone, otherwise called a frustrum. The volume of a cone is 1/3 the volume of the cylinder with the same height and circular base. So let's have a look at figure 22. So here, for example, so if we take this distance here to be the height of the cylinder that it fits into, or the height from the center of this circle to the apex of that cone, then that's our height. And so down here we've got a radius, which is the distance from the center to the edge. And so the volume of the cone is 1/3 pi r squared h. So the volume of the cylinder is pi r squared times the height. So basically the volume of the cone inside is 1/3 of the volume of the cylinder. Okay, now if we were to chop off this cone at some place, can we also measure the volume of that? Well, yes, we can, and it'll be the volume, or the difference of the volume of the small cone up at the top and the larger cone. So larger volume minus smaller volume of cone. So if we now let h be the complete height and lowercase h be the height of the smaller cone. So let's have a look at the figure on the next page. So h is the full height, or uppercase h is the full height, lowercase h is oh, I said it was the height from here to here, but I suppose in this diagram, lowercase height is the height of the truncated cone, so from here to here. And so that doesn't quite agree with the formula on the previous page, does it? Because what we have here. So I'm going to have to relabel this, all right? So I'll take this. This distance here I'm going to have to call h, and this one uppercase h, and that would be uppercase h here for the volume of the cylinder. Okay, so then the difference between those volumes, now the distance from here to here, we can just give this another name like, oh, I don't know, let's call this height q, which is h minus h. Alright, so with this diagram, then this is the correct formula for the volume of the frustum, the difference here, down here. Okay, because I'm taking the larger volume, subtracting the volume of the smaller cone there, and I can factorize this, factorizing out the 1/3 pi, okay, to simplify that. However, I now see that this is the wrong diagram, or let's just say wrong labeling. So I would have to then cross out this and call this one lowercase h, and then this one is h minus lowercase h. Okay, in my way of calculating that. So I have a feeling that Lauren used the other labels in her video. Okay, so calculate the volume of the truncated cone with radius 4 centimeters, height 17 centimeters, that's the bigger height, and smaller radius up here, 2 centimeters, and lower, or this height here, is 9 centimeters. Okay, so this doesn't quite correspond to the labeling of the diagram there. So what we have then is that volume is 1/3 pi r squared h minus r squared h, where these are uppercase, these are lowercase, so we sub in the numbers and we get 247.1386, and that would be centimeters cubed. Alright, let's move on to the volume of a prism. So a prism is a three-dimensional shape whose ends are identical and sides are parallelograms. The volume of a prism is given by the area of the base times the height. Example 10.3. Calculate the volume of a hexagonal prism of height 4.1 centimeters and hexagonal base with each side of length 6.5 centimeters. So the area of a regular hexagon is given by 3√3 on 2a squared, where a is the side length. So we can calculate the volume of the prism as the area of the base times the height. So that would be then 3√3 on 2 a squared times h, and now we can just sub in those numbers, simplify, and we get 450.052 centimeters cubed. Now for irregular prisms, we can use a numerical technique to calculate the area down on the base. So remember, we would take measurements of the lengths at equal distances to get a good estimate here. So taking these of equal distance using Simpson's rule or the trapezoidal rule. and then multiply the area of the base times the height to get an estimate of the volume of that figure. Okay, now we're going to look at trigonometry, but I feel like this is somewhat of a revision because we've already been talking about trigonometry quite a lot in tutorials earlier in the semester. So let's go into more detail here formally. So we'll look at sine, cos, and tan and the multiplicative inverses of those, which would be CSC or cosec, sec, and cot. So the sign of each of these in the first, second, third, and fourth quadrant are, in the first quadrant, sine, cos, and tan are all positive. In the second quadrant, sine is the only one that's positive. Cos and tan are negative. In the third quadrant, tan is the only one that is positive. Sine and cos are negative. And in the fourth quadrant, only cos is positive and sine and tan are negative. So some people like to remember this via the acronym CAST, C-A-S-T, CAST, for cos, all, sine, and tan. So the mathematical convention of measuring angles is to measure them from the positive end of the x-axis counterclockwise. But if we're measuring the angle between two vectors, then we don't need such a convention, for example. Okay. Let's have a look at the first result in this section. Let theta be an angle. If theta is between 0 and 90 degrees, then sine of theta is positive, cos of theta is positive, and tan of theta is positive. So that's just the, the all that's up here in the diagram. Okay. If theta is between 90 degrees and 180 degrees, well then we're in the second quadrant, so sine is positive, cos is negative, and tan is negative. Now this is just exactly what we said earlier. So if theta is between 180 degrees and 270 degrees, then the angle theta is in the third quadrant, and sine is negative, cos is negative, but tan is positive. If theta is in the fourth quadrant, then sine is negative, cos is positive, and tan is negative. Okay, let's have a look at the unit circle. So that's the equation x squared plus y squared equals 1. Now we've got an arbitrary point cos theta sine theta on the unit circle for all theta between 0 and 360. This is a point on that circle. Now, what this is a parameterization of the unit circle, because I don't need two letters to describe that. I only need one letter, theta, to describe that, which can be convenient. Okay, so this length of this hypotenuse here is 1, and so x over 1 is equal to adjacent on hypotenuse, which is cos of theta, and y over the hypotenuse, which is 1, is sine of theta. And so we can write this as x equals cos theta, y equals sine theta, and then we have a description of the point xy on the unit circle x squared plus y squared equals 1. And this down here is theta. Okay, figure 26 also shows via symmetry about the x-axis. So in other words, if I take the point down here, then I'm looking at angle minus theta, and then this point down here would be, well, it's got the same x value, so cos theta but it's got y coordinate minus sine of theta. Okay, but looking at this, it's also sine of minus theta. So we see then that sine of minus theta is the same as minus sine theta. Cos of minus theta is the same as cos of theta. And also we can deduce that symmetry about the y-axis will tell us that sine of 180 degrees minus theta is the same as sine theta. We've already determined this from that diagram. And tan of 180 degrees plus theta is tan theta. Okay, note that since tan of theta is defined to be sine theta over cos theta, and cos of 90 degrees is 0, that means then that tan of 90 degrees is undefined. Let's have a look at some important identities relating to the sides of a right triangle and the angle theta shown in figure 27. Okay, so we've already done this, but so this relates to the circle of radius r. So you're looking at the circle x squared plus y squared equals r squared. Right, so the parameterization of that circle writes every point xy as r cos theta, r sine theta in the circle of radius r. And so we can write cos theta is x on r, sine theta is y on r, and tan theta is y on x. And that agrees with tan of theta being opposite on adjacent, so y over x. Cos of theta being x on r, and sine theta being y on r, opposite on hypotenuse. Okay, so to verify that, it's a little bit small, so maybe need to get the focus correct again. Okay, there we go. It's a little bit better. Sine of theta over cos of theta is y on r over x on r. And if we multiply top and bottom by r, we get y on x, which is tan of theta. Now I said that we could define tan of theta as sine theta over cos theta, but we can equally well see that that identity is consistent or derived from just the consideration of sine theta and cos theta on the circle of radius r. Okay, so next let's have a look at cos squared plus sine squared. So what this is just x on r squared plus y on r squared. Now if we expand that, we get x squared on r squared plus y squared on r squared. And since they have the same denominator, we can place that over the same vinculum or fraction bar. So that's x squared plus y squared on r squared. But since x squared plus y squared is r squared, this is just r squared over r squared by Pythagoras. And so that gives us 1. So we've deduced that cos squared of theta plus sine squared of theta must be equal to 1. Okay, other identities that are occasionally useful, cot, which is the multiplicative inverse of tan of theta. So inverting sine over cos gives us cos over sine. Now sec of theta is 1 on cos of theta, and CSC or cosec of theta is 1 on sine of theta. When we write positive powers of trig functions, we abbreviate those as, say, sine superscript n of theta, but what this means is sine of theta to the power of n, etc., right? However, when we put sine superscript -1 of theta, etc., in the calculator we mean this to be the multiplicative inverse, and we mean this to be the inverse function, not the multiplicative inverse, right? So the multiplicative inverses of each of those are up here. These mean inverse function. Otherwise, we can call these arc sine theta, arc cos of theta, and arc tan of theta, respectively, for the inverse function. Okay, so in general we don't have this here being equal, because this on the left refers to the inverse function, this on the right refers to the multiplicative inverse of the function. Alright, let's move on to the next page. So we have an example here. Find all theta satisfying sine of theta is 1/2 and theta is between 0 and 180 degrees. Okay, so applying the inverse function to both sides, we find that theta is arc sine of 1/2, which is 30 degrees, but sine of theta is sine of 180 degrees minus theta, so we could also have 150 degrees as an answer. Okay, so that shows us then we have two answers in this range, 30 degrees and 150 degrees. And so I always like to draw a little diagram of this. So here we've got 30 degrees. But over here, so if this is 150 degrees, then the angle from here to here is 30 degrees, right? In exact symmetry about the y-axis. So 180 minus 30 is 150 degrees. And we see that we would get the same sine ratios for these two triangles in there. Okay, next we have another useful identity is the following. 1 plus tan squared theta is sec squared theta, but this comes from cos squared theta plus sine squared theta equals 1. Since 1 plus tan squared theta is 1 plus sine squared theta over cos squared theta, we're just squaring sine over cos. Okay, now if we represent 1 as cos squared theta over cos squared theta, then we have this, and now we have the same denominators, so we can add the numerators and place that over the same vinculum. So we've got cos squared theta plus sine squared theta all over cos squared theta, but the sum of those two is equal to 1 because cos squared theta plus sine squared theta equals 1. So we have 1 over cos squared theta, which is defined as sec squared theta. So similarly, you can show that 1 plus cot squared theta is CSC squared theta, or cosec squared theta, using the same trick. Okay, let's have a look at an example. Solve the triangle with side lengths B is 12, C is 10, and the angle opposite C is 35 degrees. So we've already done a demonstration of this, I'm pretty sure, in the previous lecture, as in the cosine rule. So here we're just going to apply the cosine rule and the sine rule to solve this problem. So recall that A plus B plus C is 180 degrees. We have the cosine rule there and the sine rule there. Okay, so B is 12, C is 10, and uppercase C is 35 degrees. So first, rearranging the sine rule, sine of B is side length B over side length C times sine of angle C. We have angle C. We want to get angle B. So 12 over 10 sine 35 degrees gives us 0.68829 and so on. Now taking inverse functions, we have 43.495 degrees for B, or 180 minus that, which is 136.505 degrees. So if B is equal to 43.495 degrees, then A would be 180 minus 43.495 minus 35 degrees, which is 101.505 degrees. And then, so using the cosine rule would give us that lowercase a is 17.0842. Now if B is equal to 136.505 degrees, then we get 8.5 degrees or so for angle A, and side length A is then 6.631 degrees. So taking square roots gives us 2.575. Or sorry, I think I said degrees, but that's a side length. So we see that there are two distinct possibilities for triangles in that problem. But they're not always, and usually what goes wrong in order to discard one of these is that A plus B plus C equals 180 degrees, and so sometimes you find that you get the contradiction that one of the angles is negative. Okay, so the last thing I want to show you here is plots of the various trig functions we've talked about. So here we have sine of x. So it starts at 0, comes down and meets the top again at 360 degrees or 2 pi radians. Then we have cos of x. It starts at the top, comes down and repeats again at 2 pi radians or 360 degrees. And then this one is a plot of tan of x. And you can see that it has vertical asymptotes. Remember, cos of 90 degrees is 0, so tan is undefined at 0, so this must be about 90 degrees where it has this vertical asymptote, or pi on 2 radians. Okay, and likewise here, so this would be 3 pi on 2 radians, or 270 degrees where we have a vertical asymptote in the plot. Alright, now here what we have is CSC, a plot of cosec. Remember, this is the multiplicative inverse of sine. Okay, so when sine is 0, CSC has a vertical asymptote. So 1 on sine of x would be undefined. Likewise here, when sine is 0, 1 on sine is undefined, and so we have a vertical asymptote. Okay, the next one, so hang on, I'll label this. So this is CSC of x, which is 1 over sine. Okay, this one is 1 over cos of x, which is sec of x. Now when cos of x is 0, we have a vertical asymptote in sec of x. Likewise here we have a vertical asymptote. Okay, and this one here is 1 over tan of x, which is cot of x. So when tan is 0, we've got a vertical asymptote in cot. This cot would not be defined when tan is 0. Alright, now these down here are plots of the inverse functions. So this is arc sine of x, which you know on the calculator as sine superscript minus 1 of x. But I'll draw your attention to what this is. So if we take the sine function back this way, okay, and consider it from here to here, and think about horizontal lines intersecting this segment, right? So if you carried this on down this far, then a horizontal line would pass through twice through that little bit. So if you want to avoid that horizontal line passing through twice, you consider the region from minus pi on 2 to pi on 2 radians, or minus 90 degrees to 90 degrees, and you reflect this about the line y equals x. And this is what you get, right? You get this plot when you reflect that. So of relevance here is the line y equals x. So in other words, arc sine of x is a reflection of sine of x, or the equation y equals sine of x, between minus pi on 2 and pi on 2 radians about the line y equals x. Okay, now let's have a look at the next one. This is arc cos of x, which you would know as cos superscript minus 1, or the inverse function of cos. And this one right here is arc tan of x, which you would know as tan superscript minus 1 of x. And likewise, these are reflections of, so arc cos is a reflection of a cos function about the line y equals x in some range that such that horizontal lines don't have two intersections. Okay, so I hope that was a little bit insightful for you.